a lot. Yeah, so what I'm going to talk about today is a sort of full system stack kind of approach to quantum computation. And in particular, we're looking at building a very optimized domain-specific sort of language and software stack to go from algorithms to machines. Right? And this is the emphasis of this project, which you got the acronym right. It's Enabling Practical Scale Quantum Computing, or EPIC. And it's a really sort of exciting collaboration between theory people at MIT, computer scientists at Chicago, and sort of device people at Chicago and Duke, and education people at Santa Barbara. All right. So since this is, I'm guessing, a fairly quantum-friendly crowd, I'm not going to do my sell of why do we care about quantum computation. But I will start with, we're in this pretty exciting time, right? Which I think I think John Preskill is right, that it's a sort of a historic time that we're going to have these machines, which these are all still being tested, really. But we're going to have these machines that are of a scale that we can't simulate, right, on classical machines. So we're definitely going to have a lot more understanding of how machines work. And hopefully they're also going to be of a scale in which we can actually solve interesting problems, right? And so as a computer scientist and computer architect, I often look back at the 1950s in computer science in sort of machines, right? And I think, if only I had been alive at that time, everything I did would be new, right? And so that's essentially where we are in quantum computation, so it's a really fun time to be working on this. Okay, that being said, so the emphasis of this, of our project, and I think of many people around the world, is this issue that, if we look at the algorithms that we traditionally care about and the machines that we can expect in the next, sort of 5 or 10 years, there's quite a large gap between, if we just look at qubit count, right, in terms of what you need. And so, luckily, there are some algorithms that might be interesting that require a much more modest number of bits. But still, there's a pretty substantial gap of maybe 3 orders of magnitude between these algorithms being usefully run and the machines that we expect. Right? So what we believe is that we can, with sort of careful design of the software stack and maybe some redesign of the hardware, make the mapping from these algorithms to these machines much more efficient. Right? And so we're going to look at this fairly traditional software hardware stack, and we're going to actually look at, the way that we're actually going to be more efficient is actually by breaking through those layers of abstraction and those layers of the stack, and actually expose much more of the device properties up to the languages and the software and the compiler. And we have this pretty aggressive goal in our project, which is sort of what got us the expedition, which is to say we're going to get 100 to 1,000x more efficiency. All right? Sounds pretty aggressive, but actually you'll see, I'm going to give you a whole bunch of examples of things we've done and we plan to do, and I hope that people help us do, that will give us that greater efficiency. And the sort of the punchline of having that greater efficiency is that amounts to about 10 to 20 years of building better machines. Right? And so if we can actually get 100 to 1,000x greater efficiency, we can run these algorithms on these machines much sooner than if we didn't, right? And one thing I should clarify is when I talk about greater efficiency, I've sort of shown this in the sort of easy way of just number of qubits, but it's actually number of qubits and number of gates and the reliability that you need from those qubits and gates, right? So those are the 3 dimensions upon which we focus in terms of all our optimizations to get this greater efficiency. Okay, so now I'm going to give you a whole bunch of examples, okay, of things that you can do if you break through that stack and you make, you make the machine more visible to the software and how much more efficiency you can get, okay? So the first one is compiling programs directly to control pulses. Now, I showed you that stack. So on the left side of this picture is sort of the way we used to do things, right? Sort of the way that most people do things. And that what we do is we take a program, in our case is written essentially in C with some special quantum instructions, and we compile it down to essentially quantum gates, or some logical set of quantum gates, which we call quantum assembly. And then we compile that down to a machine-specific set of gates, right? And then we compile that down to a series of control pulses. In this case, microwave control pulses for a superconducting machine, but it could be laser pulses for a trapped ion machine, right? So this is the old way. Okay, so the new way is basically we're going to take a set of quantum assembly, a set of gates, and we're going to group them together into, say, a 10-qubit operation, like a 10-qubit function. Right? So we can do a whole bunch of things at once, and this is this aggregated instruction. And then we take that and we feed it to the grape tool, which is a gradient ascent tool, which basically treats the function as a start state and an end state in a high-dimensional space. And this basically searches for the shortest pulse sequence it can to get from the start state to the end state. Right? So here's an example. Right? So here's a simple optimization circuit, QAOA. And we break it into these three pieces. Okay? And then if we just look at this middle piece here, if we took each gate and we translated it separately into pulses, it would look like this. All right? If instead we take this and we feed the whole thing to grape, it looks like this. Right? So it's about 3x shorter in time, right? And it's a simpler. Right? Okay, so this is an interesting thing, right? It's basically sort of just we pay the cost of not having this nice common interface, which is the quantum assembly or quantum gates. Instead, we have to expose the pulse interface, which interestingly IBM has exposed as something called open pulse, right? And then we try to program the machine directly. Okay? And yeah. It's automated. In fact, so today okay, so I should go back. This is, in the computer science world, we have this ASPOS, right? So ASPOS is a conference, one of our systems conferences, and the paper appears there and on the archive. And so, in fact, this separation is actually our contribution. The ability to do this sort of existed in this tool Grape, but it only scales to 5 to 10 qubits, right? So what you have to do is you have to do this in a smart way, and there are a number of things that have to happen. You have to be careful about parallelism, and you have to be careful about, you can optimize by commuting operations and things like that. So the compiler actually does a whole bunch of things to get those blocks. Okay? So once you get those blocks, then you can do a nice job of this. And I'll just give you a little bit of a summary here, since I'm like showing 4 projects today. The interesting thing that we found was, so these graphs are, you start with the old way, which is every 1 and 2 qubit gates, right? And we aggregate to the right, which is we make bigger and bigger blocks, okay? And then this is the speed up from the base case. So how much faster are we as we go to the right? Now what's interesting, if you take a look at these, mostly arithmetic circuits and some chemistry circuits, what you find is that some of them are more parallel in their execution, and some of them are more serial. And the more parallel ones actually tail off quicker, right? Because what happens is when you get blocks that are too big, you accidentally sequentialize the circuit, okay? And so if you had a lot of parallelism, then that's going to hurt you, and then your speed up sort of bottoms out, okay? But on the right there, you have the circuits that are more serial, and this approach actually works better because you can use bigger and bigger blocks, and it scales better and better, right? Which it does eventually tail off. Part of that is also because the Grape tool cannot find a good solution after a while. Okay, so I think this is actually one of the approaches that I think I'm most excited about is this direct-to-pulse thing. It's interesting because it breaks the abstraction of this gate abstraction, which we, as architects, think of as the instruction set architecture. It gives us about 6x decrease in latency in what we looked at, up to 10x. It's especially useful. This was done on Dave Schuster's machine at the University of Chicago, and it uses a lot of swaps. on that machine, and the swaps actually get optimized really well into the pulse sequence. And we're planning to run this on IBM machines using their open pulse interface probably this summer. And eventually, when we get a trapped ion machine that can support arbitrary pulses without hand programming, we will also run it on a trapped ion machine. Right? So that's the first example. And like I said, what I'm going to do today is show you a whole bunch of examples of like, sort of 5 to 10x increases in efficiency, which we haven't really composed yet, but we hope to, in the life of the project, compose them all together. Yeah. Yeah. Yeah, that is an interesting question. Probably not. Well, it depends. You could, but probably not in the sense that this pulse optimization can also include like the noise model for the specific machine and the connectivity and the communication. So it's nice because it optimizes many things at once, right? It's also bad because it's complex, right? And so it's very expensive. In fact, the next, I don't have it on here, but the next thing that we're working on is a way to incrementally compile, because this is like 1 to 10 hours of compilation for one run of the circuit, right? But if you look at an iterative, like a VQ variational algorithm, you're going through thousands of iterations where every time a few parameters change. And so we're working on like partially compiling that and then fixing up the parameters and doing that much faster. All right. So here's another example of exposing the machine to the software and in the upper layers of the stack, right? What this work is it's optimizing for a specific machine, right? A specific number of qubits, specific connectivity, and the quality of the qubits and the quality of each connection on that day, right? So if you look at the IBM machines, they calibrate actually twice a day. They publish their data once a day. And you look at the calibration data, you can see that the quality of the qubits, here's like 4 qubits, varies every day, right? And it's not even the case that the same qubit is always the worst, although the orange one is pretty bad and the blue one is bad. But so these are, so the variation in qubits. This is variation in 2-qubit operators, so the coupling between different qubits. And you can see, once again, like different ones have much different error rates, right? So the gate error rate up is bad, right? So what you see is day to day it varies a lot, and it's very different for different qubits and different connectivities or couplings. So this is, once again, another ASPLOS paper that just appeared, which you can find on the archive. And what we're going to do is we're going to use a generalized solver. So it's an SMT solver, which is a satisfiability modular theory solver, which is sort of a SAT solver generalized to constraints. And so we express all this in terms of constraints, and then we run it through the solver. Okay. So what will the solver do? What it will do is it will avoid bad links and bad qubits. Right? So we're given this, so this would be a mapping of this circuit on this machine, physical machine, without worrying about the bad links, which are the red X's, and the bad qubits, which are these gray guys, right? And here's a mapping which avoids all of those, right? And so the result is here, this is compared with the native IBM software, QuizKit. Right? And then we have 2 versions of our software, one which optimizes for time, so shortest depth, or number of time steps, one that optimizes for reliability. Okay? And what you see is that, okay, up is better. That's the success rate, meaning if you take 1,000 shots, typical on an IBM machine, how many of them have the correct answer, right? And you see that's substantially better, right, than the native IBM software. Average about 3x, right, up to about 18x better reliability. At the moment, it doesn't scale, or that version of it doesn't scale very well, so it gets up to about 500 qubits, which is actually pretty far in the future. But at some point, you know, the SMT solver is high complexity, right? And it's gonna run out of your compute time to get us the solution. But it is the case that it turns out that scalability is for optimizing for the global reliability of the circuit. If instead you optimize for every time step independently, locally, you get about the same result, actually, and then you can improve the scalability by about 1,000x. So that can be fixed. And then there's actually a follow-on paper. This work was done with Princeton, and Princeton is has actually, it's going to appear in June, has a new paper which is running this system on both the machine here and the Rigetti machine. And I think the result is basically that you know, this method beats all of the native software of all three machines. Although it's not 18x better, because the trapped ion machine is essentially more reliable. It's like more consistent, right? What this adapts to is variability. I think it's pretty small. Norbert ran the experiments. I'm not on this paper. I think it's less than 10. Oh, well, that's a different, like grape. Yeah, we haven't done grape on that machine. Yeah. It's true. That's right. We could just run grape, except that Norbert won't program in our call sequences by hand. I asked him. He's like, but I would have to program in like hundreds of things, you know. So that experiment is waiting for probably Jengsang's machine to support programmable interface. Yeah, how do we do that? Or? Yeah. That's the previous one. Right. That's right. They publish that every day. We would need to have that. I mean, the whole point of this particular work is to adapt to the irregularity or variation in the machine, right? So we have to know what the variation is, huh? It's somewhat stable for the day. You know, there are some sensitivity results in the paper where they looked at, well, how often do we need to do this kind of thing? But it's actually not that stable in the day. Like if we calibrated more often, it would be better, right? But this is just sort of the first order result that if you adapt versus not adapt, but you could do better. Okay, so next one. This one's sort of neat. This is another thing where we're going to expose the machine, and what we're going to do is we're going to use Qutrits instead of qubits, right? So this paper actually came about because I think I was at Yale, and Michel Devereux said, you should look at Qutrits. and then one of my students was like, did you know that he's like, I can't believe it, in Grover's algorithm, there's this like multi-control, knot, that this multi-control gate, and it's like not one step. Like it's really expensive. Okay, so then essentially what happened was they decided, oh, how do we support things like multi-control gates? Takes a lot of Ancilla. How do we do it without Ancilla? We're going to use Qutrits instead. Okay, so essentially what we're going to do is we're going to borrow the third state in some devices. So we're not going to have more devices in our machine, but we're going to borrow the third state in some of the devices to store an Ancilla, right? So it's just so what this work does is it takes circuits that are 0 Ancilla, and it makes them much lower depth, right? So it goes from linear depth to log depth if you have 0 Ancilla, right? It's actually the case that if you have a few Ancilla, you can do this a lot better. But it's pretty interesting right now in the NISC era where every bit counts, right? And so if you don't want to pay extra Ancilla, you can really do pretty well. And the gate count, so this is the depth. The gate count is still linear, but the constant is way smaller. And so what is this, right? So if you look at this circuit, right, the generalization of qubit circuits is that this is a control on this gate, right? And the 2 basically means you have to be in the second state for that control to be true. And then this is basically the generalization of a X gate, but it's like a modulo 3, right? So you increment and you modulo. And so you can build circuits like this, which essentially, they look a lot like the Ancilla-based circuits of for example, multi-control topology. And you would basically build a tree of Ancilla, but here instead you build a tree of Qtrits, right? And so it's really interesting because Qtrits in general have been an area of speculation in classical computing for a really long time. And they really just haven't taken hold, right? And that's really because there's just an information density argument, right? It's like you get a little bit more information in each Qtrit than you do in each qubit. And there's a lot of complexity with dealing with Qtrit operators and things like that. But in this case, because the Ancilla are so critical to the depth of the circuit, it ends up being a very profitable thing to do. Right? Okay. Without Qtrits? It would look a lot like this, but the version of this would be basically twice as many qubits. You have to have n Ancilla to build the same thing, right? And we're just basically stealing n Ancilla from the Qtrits. What's interesting is we're stealing it from Qtrits, not for like Qquartz, right? So they initially did this paper with Qquartz, and I'm like, oh, come on, that's just like having the same amount of information, right? And then they were able to do it this way, so it was much cooler. Okay, but the main thing that's interesting is that if you have Qtrits, you have to go into a higher energy state, and that actually costs you because it's greater error. So besides coming up with these circuits, one of the things was to do some noise modeling to figure out, is it profitable to use the third state? And before I show you that, here's some other circuits. Here's an incrementer. And then these are just applications of the multi-control gate. Right? So these are some of the benchmark gates circuits that we use. Okay. So this is sort of the punchline, right? What's the fidelity of the circuit once you add Qtrits to it, right? And so we ran it through a whole bunch of superconducting and trapped ion models. And the models basically look at, what's the increased error rate of using the third state. And so like in superconductors, you basically have a higher photon number, so you have a greater chance of photon loss. And these different ones are basically, this is sort of the baseline model, and these are better T1 time, better gate time, better T1 and better gate time. Basically, you can't even run some of our circuits because the baseline model can't handle that depth, right? So, so for example, here, the fidelity is very low for the qubit version. And so what you see is essentially the fidelity is a lot better than the no Ancilla version, right? Because the depth is so high. And a little bit better, right, than the linear Ancilla version. So the result is basically we don't have linear Ancilla. The number of devices is like factor of 2 less. But the fidelity is pretty good, actually quite a lot better in some cases. Now, what's interesting in the trapped ion world, once again, trapped ion machines are pretty good. So the difference isn't as much, right? Like you can see it's already in the Ancilla version, we have about 89% fidelity. And the dressed Qtrit is using a special encoding of the Qtrit, which is less error prone. Okay, so this is really pretty cool. In terms of, if we expose the machine interface so that we can use higher energy states, we can store more information, we can restructure the circuits, we can get asymptotically better circuit depth depending upon what assumptions you have, right? So it's a really nice result. I think it's like, it ended up being best paper at QIP, and it's appearing in our architecture conference next month. Okay. Uh-huh. It does consider the control. There's a model in the paper which is basically, it's about an order of magnitude greater gate error because you have more possibilities of gate errors in the three states, actually. So there's basically a counting argument in the paper for the going from qubit to Qtrit errors. Okay. One more. So now we're transitioning to not quite done yet. This one, actually, this is mostly done, but we don't. It's under review, so I don't have the most recent results. But okay, so here's another way to reduce the number of qubits. And as a classical person, this is basically amounts to garbage collection of qubits, or Ancilla qubits. And what's interesting about this is that, well, it's most effective for arithmetic, classical arithmetic implemented on quantum machines. So the main thing that comes out of this is that since the arithmetic has to be reversible, you have a lot of Ancilla, right? And since it's classical, we can actually reuse the Ancilla after we do a computation, but we have to uncompute the computation, right, so that the Ancilla are no longer related to the result, right? Okay, so this is a classic trade-off between saving qubits and using gates, right? And our metric is basically going to be gates times qubits, right? It's like a quantum volume kind of argument, right? And so, so this is where the results are a little bit old. These are for very large benchmarks that we had in the IARPA days. But if you look at the large benchmarks, what we see is that we can save a lot of qubits. That's the red. That's a fraction of qubits you can reclaim. But this is the amount of computation you need to increase. This is how much more computation you need to get those back, right? To uncompute those things, right? And you can see that, we get, almost 80% here, but then we have to pay about 80% here to get back those qubits. It's the unentangling part. You basically have to uncompute before you can reuse the Ancilla for the next function. With your results, yeah, that's right. Exactly. So this is the original codes were written such that they didn't always reverse the computation, right? And so they weren't, maybe you would think, like sort of algorithmic, they weren't necessarily written in a safe way, right? And as long as you don't do anything with the Ancilla, it's okay. But these codes were written like even with nested structure functions that you keep calling them and you just have more and more Ancilla. And then if you wanted to reclaim them, you actually have to basically increase the number of double the function length, right, by uncomputing part. Does that make sense? Yeah. So I think that your point of view is that you would always uncompute, right? Yeah, we can. There you go. I can show you the paper. So I think that probably the original codes would be viewed as a sort of a somewhat unsafe way of doing this, but this is if you wanted to get those back, you would do this, and then if you take the space-time product, where you just multiply those together, what you see is that for some applications, it's beneficial, right? The space-time product, bits times gates, is lower, and for some of them, it's not. It's higher. So essentially what we did is we wrote a compiler that dynamically decides, well, not so much dynamically, but decides adaptively for a program when to uncompute and get Ancilla back and when not to, right? And so because this is the extreme case of uncomputing everything, but we could just uncompute good functions, right? or things that don't take a lot of gates and get a lot of qubits back. It's also the case that this problem gets much, much harder, which is when you when you reclaim an Ancilla, it's actually in some physical location on the machine. And the next function to use it is in some other physical location. You may want to optimize the distance between those two things, right? And so that is also in this study that we just did. And so this is basically a bunch of heuristics to try to balance all of these costs. And in fact, this is related to this mapping problem, right? In general, we're always having to map our circuits or graphs to the physical machine graph, right? And we're trying to minimize communication. And it's a really interesting problem because from my perspective, and in my experience as a classical architect, there's sort of two approaches that people take, right? One approach is to treat the computation as for the whole length of the computation as a single static graph. And if you treat it as that graph, then you can use some nice partitioning techniques, spectral techniques, to give you a fairly globally nice solution, right? But that ignores what happens at every given time step, right? It doesn't think about sort of temporal locality of behavior, right? And on the other hand, people use greedy approaches, which only pretty much think about the locally optimal temporal behavior. And so the two have sort of been in opposition. So we recently just did something actually where we tried to take a whole bunch of slices and did each one as optimally as we could, and then also tried to keep the distance between the slices in terms of communication low. So there's some middle ground here that's interesting. But this gets a lot more complicated. For example, if you have, as we looked at just earlier, irregular physical constraints, like connectivity that isn't just a regular 2D mesh, right? If you have bad links and bad qubits, a lot of these techniques don't work well with too many arbitrary constraints, right? Like the spectral partitioners don't work well. Greedy ones work pretty well because they're just, step-by-step heuristics anyway. So that's interesting. And then this issue that I just mentioned, which is, there are lots of other phases of our compiler or our optimization which affect the mapping, right? For example, this qubit reuse or reclamation happens in certain locations. So we have to decide, we have all these decisions that happen, but they're all coupled together. And at some level, when we started looking at this problem anew in the last few years, where we looked at, instead of larger machines, very small machines, we got very interested in, well, we can just optimize lots of things together and get a much better solution. But even at this small size, once you sort of conflate a whole bunch of layers of optimization together, it quickly blows up in your face, right? And so it's an interesting problem to sort of decide which things to do together, which things to maybe iterate, right? Our compiler is like a layered sort of pass-based thing, where so you do one optimization, you do the next, and you do the next. You might loop back, but they sort of don't inform each other very well, right? So that's a sort of, this issue of cross-layer optimization is a very traditional classical issue, right? And it quickly blows up in complexity. So this is one of those places. Okay, here's another one. So you're probably aware of, like, there are a lot of nice ways, like IBM has these nice papers where they looked at essentially statistically creating better results, dealing with measurement error and sort of factoring out noise, right? And then on the other end, there are like some very extreme cases where people use learning to adapt to device noise and get like better fidelity in devices by modeling the noise and then sort of coming up with a control signal to compensate for that noise. But the problem with these approaches is that they require too much measurement, right? And they're not practical. And so some of the work that we're trying to do now is, in the classical world, there is a sort of fusion of learning and control algorithms, right? And so learning allows you to approach a very high complexity problem, right? But at pretty high time cost and data cost, right, to learn that problem. And then the idea is to learn initially and then create sort of control algorithms that will adapt dynamically to changing conditions and not have to recalibrate very often. And this has worked pretty well in classical systems. Not clear, we're still at the beginning of whether this is going to work well in quantum systems. Okay, so now I'm going to switch gears for a little bit. I have mostly talked about performance, right, efficiency, right, and how to fit programs onto machines. But actually a fairly large part of our expeditions project and a big concern of ours is how do we get this right, okay? And this really comes up because we're in this fairly ridiculous bootstrapping situation here, right, where, you know, we're going to have machines that barely work and are pretty small, and we can't simulate them on classical machines. And we're going to have software that we cobbled together, but we've pretty much not really had a chance to test, right? So we're going to run our program on our machine, and we're going to get some errors, and we're not even going to know, you know, did that come from the algorithm, from the compiler, or from the machine, right? And so, you know, in the classical world, we've had these formal techniques and technologies for trying to verify software and hardware, right? But they're really not that popular because in the classical world, you can always punt and say, oh, that's sort of hard. We're going to just test it, right? We're going to run it a few times and see if it looks okay, right? But we're basically not going to be able to do that here, right? And so it's, in some sense, it's, for better or worse, it's the perfect place to use more formal methods, right? But there's a very fundamental issue here, right? And that is that, you know, if we are checking for properties that are too similar to the actual computation, right, we're essentially reducing the problem to simulating the computation, right? And we know that, at least for algorithms that we care about, that's going to be really hard to do classically. And so fundamentally, the question is, can we define properties that are not too similar to the computation that we can check in sort of polynomial or at least exponential with very small constant or something like, you know, something practical that is useful to giving us some information about whether the program or the software is correct, right? You know, we're still in the beginning of this. I mean, sort of, long ago, there was lots of work in this, like we can check for no cloning. That's not too hard to do, actually, right? But much more subtle things, you know, we have defined properties many of which actually just require simulation of the quantum state, which isn't really that helpful. And there's some nice theory work. You know, Aram Harrow has some work on assertions. So there's some nice assertions that we can do. Actually, I think Princeton is just coming out with a paper on some sort of statistical assertions that I think is nice. So anyway, but this is a big area, you know, I think, going into the future of, you know, and a hard area. Yeah. It's both. I think there are many aspects of this, right? The one that we're sort of focusing on is, let's assume that the algorithm is correct, right? Someone has an algorithm. How do you express it? And then how do you compile it and optimize it down to something the machine can run? So that tool flow has a lot of steps, right? And so verifying that is interesting, for example. That's right. And so if you had some confidence that the code you're running on the machine is correct, then you can, you know, then also ask the question of how does that compare with the actual run on the machine. Right? And when I first started this work, I really wasn't that interested in quantum simulation, but in the end, I had to go there, right? And you know, quantum simulation is really interesting because, you know, at one level, it establishes the baseline for quantum supremacy, right? So basically, the bigger the simulation we can do on a classical machine, the harder it is to build a physical machine that we can claim quantum supremacy for, right? And that's sort of, there's this contest going on. And there have been a number of techniques out here. So there's this Intel quantum simulator, which they ran on large supercomputers. It got 45 qubits of general simulation, which sort of defines some baseline. And then there are some approaches which essentially focus on the quantum supremacy problem, right? Shallow random circuits using tensor contraction or Feynman path sampling, which can get you a fairly large number of qubits, right, in the 50 or 60 qubits or something like that, right? Maybe larger. I think this paper says they can get to 80 if you spent like $10 million on the cloud. It's like they actually did a financial calculation of how many samples would it take, so it's scaling out. Yeah, we have some work with Argon where we've actually used data compression to compress the state vector so we can fit it onto their largest machines. And then that can actually run about 59 qubits right now with some fidelity loss. So this is a whole area which is both interesting from the standpoint of quantum supremacy, but also from the standpoint of testing your code, right? So if we can run non-trivial sized Grover's algorithm, we can sort of actually test it a little bit, right? It's not formal correctness at all, but it gives us at least some means to test the behavior that we expect. Of course, this gets a lot more complicated if we want to simulate noise. None of this does this, right? But we're also interested in that. So along those lines, I think another interesting direction is, developing tools to help the programmer, right? And actually, for many years, I used to go ask my favorite algorithms people, could we come up with some tools to help you create more algorithms? And they would basically say, no, that doesn't sound too reasonable or useful. But eventually, I figured out that the hard part in terms of tools was if you have the algorithm, which is, sort of typically more of a theoretical sketch of the implementation, it takes about a year or two to implement that algorithm on a machine, right? And so it depends, but and we find that process is extremely error prone, right? And so just taking sort of a kernel or a core algorithm and turning it into an application is a big deal. And so there's some notion of, we should create tools to make that easy, right? And so one notion might be visualization, and maybe visualization of resource usage, of entanglement, sort of qubit usage. Those might give some feedback to the programmer in terms of how their implementation is doing. More sort of practically, we might expect more specialized libraries and building blocks written so that you can easily just piece together your own applications, which I think, Circ and OpenFermion and these other sort of industrial efforts are good examples of that. And then just sort of a more crazy out there idea is that I'll talk about the idea of program synthesis, which is basically from a sketch of a program or a specification automatically generating an implementation, right? Which is hard to do, but maybe not harder than writing correct code and verifying it. So this is a little visualization that one of my students created, which is for HHL. So over time, for different functions, parts of the circuit, how much pairwise entanglement was there in those qubits, okay? So like one is like they're all entangled, and so it sort of converges a little bit here. It's interesting. So when I saw this, I thought two things. One is, I sort of thought, well, I thought maybe it would be higher, right? So but then I thought, well, actually, it's pretty high, right? Like, you're mostly in the sort of 50% range, which basically says if you try to simulate this, it will be hard, right? Because, it's like exponential of a constant factor of 2 in there, What is interesting about this is maybe it shows maybe a little bit of promise in terms of approaches that might maybe cluster. I don't know how clusterable this is, but it says that not everything is interacting with everything, right? So there are a number of implications here, but one of them is maybe, also looking at this might tell you something about whether you wrote the program correctly, right? If this is what you expect. Right? So a whole bunch of things like that. Let me just show you one last crazy thing, which is this is something in the classical world, which came about in about 2006, which is this idea that you can just sort of specify what your program wants to look like, and then you just essentially randomly generate programs, and then you test them to see if they meet the specification. You just keep going, and then out comes the program, right? And they actually have improved this quite a lot since 2006. They use sort of, the verifier has some knowledge in it, essentially, of what the program should look like. And they use that to guide the synthesizer, so it's not just totally random what it generates. And this actually works really well for special, small, domain-specific languages. For example, they use it for network protocols or security protocols, like little policies they want to write. They can synthesize correct programs without having to implement them. Okay? So the idea here is in the quantum world, this might be interesting because, one, we are a very small domain-specific language, right? And our programs are small, typically. And what's interesting is this is essentially an exponentially complex thing to do. But verifying quantum programs is also an exponentially complex thing to do, right? So the idea is maybe it's easier to go forwards and synthesize a correct program than to have a person write a program and then go backwards and verify that it was correct. Right? Maybe. So I had a student play with this. He hasn't really done this for, so communication protocols were easier, so he did this for teleportation. And what was interesting was he generated a teleportation protocol that was something that no human would write, right? It's like strange fractional things like that. And so he was interested in this because he thought, oh, maybe I could generate new quantum algorithms. I don't know, maybe. He's got a lot of ideas, so he hasn't gotten to follow this up yet. I think it's interesting just if you could have a correct path from specification to implementation. But it does allow you to maybe experiment with, things that people wouldn't consider, like a person would not consider. All right, so I'm going to wrap up now after my whirlwind potpourri things. In the end, I think where we really are right now is trying to figure out what are the right abstractions for quantum computation and in this sort of system stack, and what are the right things to break, right? And so where we are is we have some abstractions already, right? So we have, people use this proof language to specify programs to see if they're correct. We might even use a fairly physical model of what programs should do and try to verify that. We have a whole bunch of programming languages out there already, right? We have, most people use some sort of quantum gate set, which is some form of quantum assembly, which now is somewhat standardized, I suppose, because IBM has OpenQASM. But basically all the QASM dialects look pretty much the same within some annoying variation of like arguments different or slightly different semantics. But in general, if you just write a little translator, you can run between all the different software stacks. And then what's neat now is we even have a pulse interface, which I think is an open question as to how generalizable it is. It's designed for IBM's machines right now, and it's intended to be usable for other technologies, but we don't really know yet how well that will work. So this is where we are. It's probably a little premature to actually fix any of these interfaces, right? But it is useful to have them because it allows us to experiment and interoperate. But I think what I hope I've shown you in our work is that it's really about where should we break these, right? That's where we're going to get the 100x or 1000x efficiency that we're looking for. Mm-hmm. It's both, right? A lot of the architecture work, I would say, is focused on the cost of communication, right? And the fact that you're going to have some physical layout that's generally two-dimensional. I mean, sometimes one-dimensional, but we'll say we have like a 2D sort of distance metric. And so a lot of the work tends to be in that area. There also tends to be so that's a little bit general, but there also tends to be a fair amount of work in sort of technology-specific things, right? And right now, actually, I didn't talk about it, but I would say a really big area is classical control of quantum systems, right? There's not enough work being done there, and I think that's a huge way of increasing the reliability of these machines, right? I think that's already being done in IonQ, but I think there just aren't that many classical sort of embedded processing, control, and sort of mixed signal analog circuit designers working in this space, right? I think it's mostly physicists training themselves to do work in this space, right? And it would be really great if we could get the people who like build these systems for, you know, cell phone base stations or whatever optical, you know, communication systems, right? These people should be working on our system. Yes, yes, we do expect that. And we're even like working on, for cold systems, we're working on superconducting circuits for cold control, actually. So at the beginning of this talk, I talked about this gap between algorithms and machines. But I think there's this sort of interesting gap that we have to deal with, which is a gap in time, right? Or actually in scale, both in time and scale. So 15 years ago, the work that we did in this space was very theoretical. And essentially, what can we do for like 100,000, a million qubits? How can we write compilers for that? You know, one day when we have these machines, what will that look like? Then suddenly machines show up, and we're like, oh, we're going to be here, and we're going to look at how to very, you know, deeply optimize for small machines and their irregular properties, right? So the question is, when this also happened in classical machines, and eventually classical machines got over here, right? And bits were free, instructions were free, essentially, right? And we didn't worry about those things anymore. So the question is, what are we going to, the things that we learn in the next 5 to 10 years in this space, how are they going to carry forward as things scale, if we optimistically think that things will scale, right? I think actually quite a lot of what we learn here will generalize. I think it would be hard to imagine a future in which qubits were free, right? I mean, we may have a lot of them, but you know, I think we're still going to be fairly conscious of using them, and gates probably. And so a lot of this sort of domain-specific exposure of physical properties, I think, will persist at some level. And in the end, it will come down to like which abstractions, like what things do we think are important that we will continue to expose, right? And so, and even classical architectures are backsliding, right? Classical architectures are now starting to expose errors and variability at some level, right? And power constraints, for example. So physical details are sort of going back and things aren't free anymore. Finally, this is our project website. It has all the software that we use to do these experiments. Maybe it's a less of an issue in this for this audience. Usually when I give this talk, I'm trying to convince classical people to work in this space. And I say, go here, look at this software, and look at the videos of like Peter Shor lecturing and things, you know, telling you about these algorithms. And so we have a tutorial that we run, and it has like it's a system that goes from our compiler to QuizKit to the IBM machines. And it has a whole bunch of Jupyter notebooks that are structured for people to play with it, essentially. That's sort of the entry level, and then, you know, the different optimizations I talk about are, you know, are then going into the open source compiler infrastructure and modifying. So finally, let me wrap up. You know, once again, I think that, you know, we're at this really exciting historic time where there are a lot of opportunities. And I think that the key thing is, you know, how do we break these abstractions, and what things are we going to expose? You know, what complexity are we going to deal with, right? Right now, a lot, right? We're just exposing everything and trying to get as much as we can. But at some point, you know, we're going to have to pick and choose and decide what are the right things to keep in our infrastructure and to carry forward. All right, thanks a lot. Mm-hmm. Certainly, certainly. I mean, right now, we've been working at a fairly low level, so we're sort of informing the compiler with physical details in the machine, but there certainly are, certainly in the classical world, it always happens that there's program, like sort of application knowledge that you should be communicating down, right, into the tools. We haven't done a lot of that yet. Partly it's because there aren't a lot of quantum applications, right? So, and a lot of them that we're working with, we understand pretty well. But I think that there's this idea of pragmas, but then there's also this idea, I think, maybe more importantly, I think we need a more abstract way to express algorithms that's easier to do correctly, right? That's closer to the original mathematical expression of the algorithm, I think. And then an automated way to translate that into an implementation. Right? Like right now, we basically take an algorithm and we write it in a circuit description. Right? It basically looks like hardware description language. And it's very detailed, and it's very easy to get wrong. Right? And so I think there's some gap there, that really needs to be addressed. Yeah, I think what you're saying is sort of, is there any focus on sort of less computational tasks that are more like embedded or control tasks? There is at Chicago, right? So Chicago has this Institute for Molecular Engineering and this Chicago Quantum Exchange, which is all the labs and universities in the area. And they have a pretty strong focus on communication and sensing. And then there's a focus on these like simpler control tasks, basically. Our work, this particular work, and I think, the sort of computer science systems emphasis that we take is much more focused on more general computation. What was that? So that was actually in the primary conference, but we run tutorials, and actually in June, which is the Federated Computing Conference, we're running like an industry summit thing that FCRC asked for. So most of the machine builders will come and talk about their machines. And then there are also, all those people are actually on our advisory board, so then they're going to come and we have an advisory board meeting. But the public part of that is there's going to be a morning where there will be talks from IMQ and Intel and Google and IBM and Microsoft, Rigetti. This will be in Phoenix. So it's TLDI is there, I think. It's every 4 years they do the Federated Conference. So it's there. Did you have a question? Huh? Yeah, program synthesis. Yeah. The sketch is really just constraints, and so the original sketch was like very like pseudocode, just like a barely, like not all the statements in a program, but like a few statements that sort of show, what the program should look like. I mean, you could start with just nothing and it'd just be totally random, right? But it's like a skeleton of a program. And then you have to have some specification of what the input and output conditions are so that you can check whether it's doing the right thing. So that's what the sketch looks like. Yeah, he had basically just a functional description of what it should be, and then I think just sort of like what the inputs and outputs were, and maybe he put something like there would be some generalized operator here, here, and here, and then just had the machine search for them. I think maybe not as much. I mean, honestly, I'm not really that great at that history, but I would, we know that they had sort of vacuum tubes and eventually transistors and like core memory, magnetic cores, things like that. They tended to not be so, there weren't so many technologies at once, right? They were sort of like there would be an established technology and then one would painfully replace it, right? And everyone would be like, we'll never use that next technology because no way it's going to work as well as this one. And then eventually it would disrupt the old technology. This is more comparable to, for example, memory technologies. So over the last 10 years, there have been a lot of different memory technologies, especially for non-volatile memory, and a lot of competition. So it's sort of comparable to that. Mm-hmm. Yeah. Yeah, I mean, right. I mean, that happened over at least 20 years, right? And then beyond that, it was probably another 20 years of making transistors cheaper and cheaper, right? 30 maybe. So but I would say probably the first 20 years is where the greatest paradigm shifts happened, right? So you started out like writing, assembly code or microcode and optimizing for everything, and eventually we got better compilers, and the compilers had more resources to work with, so that people wouldn't write things by hand, right? And then eventually we got to the point where we had enough memory and enough processing power that we stopped worrying so much about every bit and every instruction. And then eventually we got to the point where we didn't know what to do with the transistors. Right? There were like too many. So now we, in the classical world, everything is about, we're going to put a widget on here is special, like specially accelerates this one thing, right? Because we have lots of transistors, and we can't even run them all at the same time because there's too much power, so we just put a whole bunch of options on the chip. Yeah, it's really picking up. So it's, in particular, so my area is sort of computer architecture, computer systems. And I would say that over the last 15 years, maybe every third conference there would be one study, pretty usually from my group, about this. And then last year, I gave the keynote at this conference, ASPLUS, which is Architecture, Programming Languages, and Operating Systems. And there were no quantum papers. And this year, actually, Krista Savore from Microsoft gave the keynote. And there were 5 quantum papers. And then it turns out there are 5 at our next conference in 2 months also. And I think we suddenly went from like almost 0 to essentially a regular session in every conference of ours, which I suppose matches the amount of hype that's going on. But also because actually we ran like 6 tutorials in the last year to sort of give people access to the kinds of problems that are interesting and infrastructure. And so we're trying to create competitors.